In this video, we're going to use the Equinox deep learning framework in JAX together with the gradient processing framework Optax, all in Python, to learn a simple neural network that mimics the sine function. For this, we will create some artificial data that somehow looks like a sine function. Then we will define our architecture by subclassing a module from the Equinox package. Afterwards, we will use the automatic differentiation engine in JAX in order to produce functions that give us gradient estimates of the weights. And then we will implement a simple training loop that updates our parameters such that ultimately the network that we get predicts something like a sine function. Let's get started. Hi and welcome to this new video in this series on training neural networks to mimic the sine function in various frameworks and languages. This time in particular we want to use Equinox, which is a recent framework built upon JAX and uses a very low-level abstraction for neural networks. Let's start right away by our imports. So we will need JAX, then we are also importing jax.numpy as JNP. Then we will of course need the Equinox package, which we're going to import as EQX. Then we will use the Optax package. Then I'm also going to import matplotlib.pyplot as PLT. And finally, I also want to import the list abstraction from the typing package. So from typing, import capital list. Let's execute that. And then let us define some hyperparameters. So for the training, I want to use 200 samples, which we're going to generate as a toy dataset. Then let's define the architecture. So here I want to use a feed-forward neural network in the style of a multi-layer perceptron. So it can be defined by its layers. It should have a one-dimensional input layer, a 10-dimensional hidden layer, another 10-dimensional hidden layers, and another one. And finally a one-dimensional output layer. Then I also want to set the learning rate to be 0.1. And then let's have our training run for 30,000 epochs. Shift Enter executes the cell. Then let's first start by the dataset generation. For this, I first want to create a general random key for the entire Jupyter notebook to make our random initializations reproducible. So let's create a key by calling jax.random.pseudorandom number key. And let's, for instance, start at seed 0. Then let's split the key into 3 subkeys. So first of all, I want to override the main key. Then let's have an X key to draw our X samples, and then also some Y noise key to corrupt the sine values. And for this, we will call jax.random.split on the key. And then with the second argument 3, we will split it into 3 subkeys. Then let's first create the Y samples by uniformly drawing numbers between 0 and 2 pi by doing jax.random.uniform with our X key. Then the shape of whatever we want to draw shall be n samples by 1, such that we then get a matrix with n samples in the rows and 1 column. And this matches the common convention in Python that we represent tabular data by batch times spatial dimension. So the batches are in the rows, the spatial dimension is in the columns, but here we only have a one-dimensional input spatial dimension. So we only have 1 column. The minimum value for this uniform distribution shall be 0, and the maximum value for the uniform distribution is 2 times jaxnumpy.py. Then let's create the corresponding Y samples. So the ground truth would be just calling jaxnumpy.sine on the X samples, but we want to corrupt it with some normal random noise. So we will do plus jax.random.normal. The key is the Y noise key, and I want to draw an individual noise for each sample. So the dimension of this draw from the normal distribution shall also be n samples by 1 dimensional. And then we will just scale the noise by 0.3 in order to not have it too crazy. So Shift Enter then creates a dataset. Let's take a look at it by plt.scatter on the X samples and Y samples. With Shift Enter, we then see, this is also what you saw in the intro, data points that approximately follow a sine curve. Next up, let's implement our neural network architecture. And for this, we will subclass the Equinox module package. And I want to call this a simple MLP class. And I said it subclasses Equinox Module. Then let's first define the attributes of that class. And this class shall be defined by its layer transitions. Let's just call it layers. And this layers shall be a list of Equinox.neural-network.linear transformations. And then we have to implement two major functions in order to have this a valid neural network module. So we need an init function, initialization function. This will be the constructor of this, and it shall take self. And then we also provide it with the layer sizes and then also a random key. Then this constructor initializes the layers attribute to be an empty list for now. And then we will iterate over the layer transitions. So our layers are 1, 10, 10, 1, but we will have 4 layer transitions in total, going from 1 to 10, from 10 to 10, from 10 to 10, and from 10 to 1. And we can conveniently iterate over the layer transitions with some clever zipping. So let's call this the fan in and the fan out, and then use a zip iterator on the layer sizes indexed excluding the last element, and then the layer sizes indexed excluding the very first element. Then in each layer transition, in order to initialize it, we need to split our key. So let's keep again a general key and then split it into a subkey and call jax.random.split on the key. It doesn't take any more arguments because by default it splits into 2 keys. And then we can append to the layers a linear transformation by calling equinox.neural-network.linear. And then we need to provide the input dimension, which is of course fan in, and the output dimension is fan out. Then I will also say use bias true. This would be true by default, but I just want to emphasize that. And as the key, we will use the subkey. This is the constructor. Let's now move on with the call function, which is executed if we instantiate this class and then apply it as a function to some input. And first of all, this takes self, and then it takes an input x. So what does our MLP architecture do? So first of all, I want to create a temporary variable with which we iterate through the layer transitions. And then basically we will go through the layer. So let's say for layer in self.layers, and then we will override the state by calling the layer on x. So basically we had linear layers, or more precisely linear affine layers in our layers attribute, and they will perform a matrix vector multiplication together with the addition of a bias. Now, in order to turn this into a true neural network, we also need to apply a nonlinear activation function. For this, we will go to jax.neural-network.sigmoid and apply this to the layer. So basically, in each iteration of this loop, we will do a matrix vector multiplication plus bias. And I see here this should not be x, this should be a. So we will do a matrix vector multiplication and a bias. And ultimately, we will then apply the nonlinear activation. But we do not want to do this in each layer, but only in the layer transition leading to the second to last layer. So let's index that excluding the last element, because for the very last layer transition, we do not want to have the sigmoid activation function, because the sigmoid is squashing our values between 0 and 1. And I want to have the last layer as a way in order to have the network learn arbitrary magnitudes. So we will manually have the final layer by saying a is self.layers at -1, so the last layer applied to a, and now without the sigmoid, and then the call function shall return a. Hit enter, executes that, and now we have our class. Let's instantiate it and call it the model by saying simple MLP. Then we will use our constants defined as layers, and then the key is the key. And if we now shift enter execute that cell, not only we will have the model initialized, but also Equinox does the parameter initialization for us. So within the layers, it uses an initialization algorithm to produce an initial parameter guess. So we could use the model to also make an initial prediction on the data set that we have. So let's call this the initial prediction. For this, first of all, I want to scatter the reference data once again, so x samples and y samples, and then we will just query the network on these x samples. So let's do plt.scatter on x samples and model applied to y samples. So this will return an error. We will see that in a second. So it runs a bit and then we get an error, says something like .general requires contracting dimensions. Quite abstract, but the idea is that if we define our MLP like this, it only works for one batch at a time. So as an input, it does not want a matrix, which is batch by spatial, but it only wants a vector, which is of size spatial. So in our case, a one-dimensional vector. And if we want to call the model on multiple batches at the same time, we need to somehow vectorize it or make it batchable. This is very easily done with a function transformation in JAX, which is called the vmap. So we will do jax.vmap on the model. So now you have to be careful here. So we will use the vmap transformation first on the model, so on our instantiated MLP class. And this basically takes the call function of that model and rewrites it in that it not only accepts a vector, but a matrix. And then we can call it on our y samples. So this is incorrect. This should of course be x samples. Then we can call it on our x samples and it will correctly work on this batched input. Let's have that shift enter. And here we go. In the orange points, we have our initial prediction. So of course, this initial prediction is not a sine function. Otherwise, we wouldn't have to train or learn the parameters. But it's also a good starting point because the magnitude of the prediction is in the same order as the data that we have. And there is no crazy oscillation within the function evaluation. So next up, we want to find the parameters to this model that produce a sine function. So first of all, we need to define a loss metric that gives us an indicator of how good we predict our data. And I want to call a function model to loss. So it shall take a model, which I want to call m here, as well as x and y. So input and output pairs. And then it first produces a prediction by calling the vmapped version of the model on the input x, so vmap on model applied to x. Then it produces the difference between the prediction and the ground truth by saying prediction minus y. And then it produces a loss by calling jnp.mean on the squared difference. And then it just returns the loss. Let's shift enter to execute that. And if we call the model to loss on our model, our x samples and our y samples, we will get an initial loss estimate. So it is 0.61. Hard to interpret, but in our optimization problem, we will then see that this loss value is decreased. And hopefully we will decrease it by quite a bit. And this gives us a good indication that our parameters to the model are getting better at mimicking the data points they see. Well, but how do we improve the parameters? As said, this is the learning problem. Learning is nothing else than solving an optimization problem. And for this, we will use a gradient-based optimizer. So we need to provide it with gradient information. So in other words, we need information how each of the individual parameter in our model, so each of the entries in the weight matrices, each of the entries in the bias vectors affect the loss. And for this, we will use the automatic differentiation engine in JAX. So we can produce a new function, which I want to call model to loss and gradient. And this one is given by calling jax.value and grad to the model to loss. So here we have another function transformation from JAX, which takes a function which produces a scalar output and rewrites it such that it not only produces a scalar output, but also produces a gradient estimate. And here by default, it will produce the gradient estimate with respect to the zero, so the first input, which is the model. So we will get a derivative with respect to the model. And here the beauty of Equinox comes in. A model is nothing else than a pie tree or a collection of variables. So it just produces another of a model, but instead of having the parameters in each of its leaves or as the weight matrices, it has the corresponding gradient entries. However, we have to be careful since Equinox allows for more complicated models than just those consisting of weight matrices and biases. Sometimes this transformation will not work. So let's try it out here. And we see it actually executes, but if you had a bit more complicated model, it wouldn't. And for this, Equinox provides a specialized transformation. It is just a convenience wrapper around some partitioning. So here we can easily use it as equinox.filter value and cred. So it is conceptually, it is the same transformation as from JAX, but a little bit tweaked such that it works with Equinox models. Okay, let's shift enter that. Then let's take a look at what it produces, if it does as I promised. So let's do model to loss and cred. On the model, the X samples and the Y samples. So basically we get two outputs. They are combined here in the tuple. So the first output is the loss value, which has the same numeric entries as if we just call the model to loss as is. I mean, this is what we expect. We do automatic differentiation, so we have to do a primal pass, so an evaluation of the function as we would normally do it as well. So we will get the loss value for free. But then, and this is important, we get a second output, which is another simple MLP instance. But if we look at the entries, well, it also has weights and biases. That's nice. But the entries are not the parameters, but in each entry value, it now has the gradient in it. And so we can use this gradient information to update the original weights and biases. So in order to do that, we need to define an optimization rule. And here I just want to use one of the simplest optimizers possible, which is a gradient descent optimizer. So let's call this deopt. And for this, we will instantiate an optimizer from the Optax package. And I want to use stochastic gradient descent. Since we will not be using any mini badging, this is exactly the same as plain gradient descent. As the learning rate, we will use the learning rate we defined as a constant. And then we can use this optimizer to instantiate an optimizer state by saying opt.init. And now we need to provide it with the collection of numbers with which the optimizer will work. So this is the collection of weights and biases. If you took all the weights and biases, flattened them and concatenated them into a very long vector, this is essentially the vector on which this optimizer works. And here again, we need to be careful that since Equinox allows for more complicated models than just pure weights and biases, I want to use one of its filters in order to extract the pure arrays that are part of the model. So we will use equinox.filter on the model, and we will filter by the rule if it is an array. So the filter function will go over the model and checks if an entry of it is an array, and then keeps it such that the optimizer only sees that. Let's shift enter that. And now we have that registered. And just for completion, this is also the point where you could change the optimizer. So here you could also use optax.atom, for instance, with the learning rate, or also some other optimizer Optax provides. And the idea is quite neat, since Optax basically is just a gradient processing library. It takes gradients, which we will produce by the automatic differentiation engine, modifies them, and then provides updates. So Optax is kind of like a middleman between the automatic differentiation engine and the deep learning framework. So the deep learning framework of Equinox defines the architectures and how the primal function is executed. Then the automatic differentiation engine transforms the primal execution to get a gradient. And then Optax takes this gradient, modifies it such that it becomes an update. So in the case of stochastic gradient descent, it will just take the gradient, negate it, and multiply it with a scalar. So because the update direction is minus eta times the gradient, and then this update direction can be used. So here, I said, this is hot swappable. You could also use atom to have something with momentum. So shift enter again to also register this comment here. Now, before we come to our training loop, I want to create a function that performs one optimization update. And I want to call this the make step function. And this function shall take the model and optimize as a state. I just want to abbreviate as opt-s. It will take x and y. And then basically what it does, it first produces the loss and the gradient by calling our model to loss and gradient on the model x and y. Then it will call optimizer. So it will capture that from the global scope, this optimizer variable. It will call optimizer.update on the gradient the opt_s and the model. This function returns updates as well as the new optimizer state. So it overrides the optimizer state because, for instance, an atom optimizer would have some small history of momenta that allow them to hopefully make better updates. Here for the stochastic gradient descent, it does not really have an state, but we will just keep it like this to follow the convention, and you can then hot swap for another optimizer. Then we can use the updates to update our model, obviously. So we will override the model by calling Equinox.apply updates on the model with the updates. And then this function shall return the model, the optimizer state, as well as the loss value. And then let's have our training loop. So the training loop, I want to collect the loss history, so basically the loss value in each epoch, into a list such that we can plot it afterwards. Then we can say for epoch in range of n epochs, do the following: override the model, the optimizer state, and produce a loss estimate by the make step function applied to the model, the optimizer state, the x samples, as well as the y samples. Then append to the loss history the loss value, and then also, just to see how our optimization progresses, print out every 100 epochs. So if the epoch is divisible by 100, print a formatted string. So say epoch is epoch and loss is loss, and then we could already execute that, but it would be relatively, and in order to get a significant speed up, we will just in time compile our make step function. And this is also the reason I extracted that into its separate function, because that kind of follows the spirit of how JAX or the JAX ecosystem works, that we have this function first approach, and we will always create like modular functions that we can then JIT compile, and to only have the relevant parts of our model being just in time compiled. So let's use another transformation. And if we were in JAX, we would do a .@jax.jit. But again, this would clash with some models that you could define with Equinox. So Equinox also provides a specialized version of that. And we will use that by @equinox.filter_jit, because our first argument is the model, and as said, this model could also contain parts which are not pure JAX arrays. And now this filter JIT will take care of it by applying a small modification here. Okay, Shift Enter that one. Now we have a JITted version of it. Then we can run our training loop. And here we go. We see our loss value is going down, and we are at epoch 20,000. Now we're at 30,000. Here we go. Let's plot the loss history by doing plt.plot on the loss history and change the y scale to logarithmic. And here we go. This is our optimization process. So we started at 6 times 10 to the minus 1, so 0.6. And then we went just below 0.1. So it's not even a factor of 10 that we reduced here. But I think it should already be sufficient to get a certain parameter state, which somehow looks like a sine function, which is the goal of this video. So let's do a final prediction of the state that we have. So let's do a plt.scatter on the x samples as well as the y samples, and then let's also scatter in the x samples together with the jax.vmap version of the model. And now this model has the updated optimized parameters applied to x samples. So let's see, here we go. We have in blue our points again, and then in orange we have the prediction. It is not a perfect sine function, so for instance also at 2 pi it does not have the value 0, but it definitely looks close like it, and there's of course way more one can do in order to ensure that it becomes a sine function. But I believe for these lines of code, for the number of lines of code that we used, it is quite an impressive result. Let me quickly summarize. So this time we use the Equinox package, which is based upon JAX together with Optax, a gradient processing library. For this we drew some random toy dataset, and then we defined our own neural architecture by subclassing the equinox.module. We defined an attribute layers in order to highlight that this will be the major part of the architecture. We initialized the layers to be linear affine transformation. by using the bias as well. Then in the call function, we had the nonlinear activation function in each layer transition, except for the very last layer transition. We instantiated the model and saw that its initial prediction is definitely not a sine function. Then we defined a function to go from the inputs and the model to the loss, which we evaluated. And then by the beauty of automatic differentiation, we rewrote that function, or we had JAX rewrite it to that a function that also produces a gradient estimate. And then we instantiated an optimizer from the Optax package, here just a plain gradient descent. But as said, you could also use the Adam optimizer. We defined a make step function, which will be called in each iteration of our optimization, so each update that is done. And the reason we outsourced that into a function is that we could then just in time compile it in order to make our training loop run reasonably fast, because in the training loop, the update mechanism, including the forward pass, the backward pass, and then the gradient processing, including the parameter update, is usually the highest computational effort. So with that, we got a significant boost in performance. And then ultimately we saw our loss decreased and we get parameter estimates that somehow mimic the sine function. This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to this channel. There are more videos on doing something similar of this neural network sine learning in different frameworks and languages. So if you're interested, then also check out those. Here you will now find similar videos, and I hope to see you in one of the next videos.